Okay, welcome to the sixth class. We actually have two more classes. Okay, and we actually have calculus and probability statistics to look forward to. So we've got quite a packed agenda for today and Monday, Wednesday. Okay, right. So on Wednesday, the key aspect is two things, right? I get you the fundamentals of mathematics. Basically, I haven't written down, but we also covered like Boolean logic, okay? But basically, these are the not even meat and potato. It's even more basic than that. It's sort of like ABC, so to speak, right? You can't speak mathematics until you realize what a number is. And just briefly recap the concept. First of all, a number is just a tag, right? It could mean nothing, absolutely nothing, just a name, right? Actually, apparently in the Chinese tradition, sometimes you name your son by a number, I think. I think in the old days, they value big family, right? So maybe you have like two sons or something, but you name the second one 7 or something, so that people think, oh, you got 7 sons. It's a bit silly, but anyway. Okay, so that's thinking of number as tag, right? What else? We can think of number as the most basic thing that human beings have been doing for 1,000 years since we started civilization and agriculture. That's counting, right? And then once you count the sheep and the goats, you also count the area. Well, you can't really count the area. You can count an area by the size. So you have to have some kind of scale. So ultimately, counting and measurement are kind of the difference is counting is in units, whereas measurement is in units of measurement or unit of scale, right? And we covered the basic concept of the 4 numbers, the 4 kind of scale, right? And they mean something precisely because the operation, the mathematical operation that you can legitimately perform. So if I ask you, what can you do with ordinal scale? You can do a lot. You can do equal, not equal, right? You can ask that. You can ask it greater than, less than, greater than, equal, but that's it. That's all you can ask. You can't perform anything else. But once you move to something like integral scale, you can add, subtract, right? But you certainly can legitimately add, multiply or divide. Because there's no absolute concept of zero. Okay, there's no fixed definition of where the zero should lie and where the negative is. And then you go to the most common use of all, okay, which is ratio scale. Okay, again, professional data scientists make the mistake that they tend to treat the value of their data as the higher scale than it is. In other words, if you get nominal scale data and you infer something like this is greater than the other one, you're wrong. Okay, the other way around is okay. The other way around, okay. If you're given a ratio scale number like the height, right? And somehow, because everybody has a different height, you call this guy, hey, hello, 5 foot there, hello, 6 foot there. Maybe you can do that. Just still treat it as a nominal scale. That's fine. But if you get a nominal scale, you treat it as equal scale, you definitely are doing something wrong. Okay? And in machine learning, that happens more often than you think. More often than you think. Okay? Right. Okay, so we talk about that, and we talk about what kind of set the number can take on, right? Basically, there are actually, you divide it into whether or not it's finite or infinite, right? If it's infinite, you further divide it into whether or not it's countable or not countable. If it's not countable, then you divide further into bounded, semi-bounded, and unbounded. Okay, so you actually go finite, not finite, infinite, countable, not countable, right? And then in infinitely infinite and not countable, you have 1, 2, 3. So basically, you have 5 words that you have to memorize. One is finite, right? Finite. 2, Countable. Countable means countably infinite, right? Bounded just means infinite, but bounded on both sides. Semi-bounded means infinite and bounded on one side. And finally, the last word is real number line. And that's infinite, unbounded, both directions. Okay, both directions. Now, technically, computers only work with countable, right? They work with discrete. Actually, finite and countable, this would belong to another way of saying this group is called discrete. The other way of saying it is continuous. Okay, it's different perspective, but that's another word as well. So you will hear something like the world is discrete. Sorry, the world is continuous. Okay, another word is analog. In other words, there's sort of like a smooth value between here and there. There's no step. There's no step. There's no step. So it's always continuous, right? But discrete is like step, step, step. Well, the way computer works is that because the computer has internal transistor that turns on and off, ultimately computer is discrete. Okay, and because it's discrete, we say we have a digital computer. Digit, right? Discrete. Okay. So when you count, say 2 finger, 3 finger, you don't count half a finger. 1, 2, 3 digit. That's exactly where the word digital comes from, your fingers, okay? So that's why computer is called digital computer, okay? Digital computer. It's not continuous, it's 1 or 2. If you know about binary, it's 001 or 000, 0010 or whatever, okay? Now that is actually something that is going to be the rest, satisfy your professional life, my professional life, till the day I die. But chances are, before you die, you're gonna have to deal with a different kind of computer that doesn't work with digital. Okay, it doesn't work with binary 1001, and you have to work with what's called quantum computer. Okay, I'm working to offer quantum computing as a class. Okay, I've dabbled with quantum computing before, but the time is not quite right to introduce. But I think within the year or two, it's going to be important that Basai has quantum computing class. Yeah, but I'm kind of like working on it. Yeah. Okay, so that's that. Okay, that's that. And okay, Boolean logic, right? Boolean logic is and or x and XOR. That's very important. And that's, by the way, it's not just important for your logical thinking. It's the way computer turns continuous number into zeros and ones. Okay, I'll just tell you quickly. It's like this. If you're adding a number in binary, right? What happened is that when you add 1 to 0, you get what? You get 1. When you add 0 to 1, you get what? You get 1. So it seems like it's an OR thing, right? 1 or 0 equals to 1. 0 or 1 equals to 1. But actually, the fundamental, most basic element about computer is an XOR gate. Why? Because when you add 1 to 1, you get 0. And then you carry 1 over to the next position. Okay? So XOR gate is the basic construction of deep down to deep, all the way down to the tiniest transistor. You have a billion in here, right? When you get down to that, it's an XOR gate. It's an XOR gate. It's kind of interesting. Okay. So after that, we took a break, right? So mid class break. And then we come back. What did we do? We started with linear algebra. Now, linear algebra, you can start to treat it as a very abstract. In fact, taking matrix theory class, it's very abstract. Vector space, mapping, and so forth. It was very, very abstract. But if you want something concrete, you have to think back to your grade school, right? 2 equations and 2 unknowns. Okay? Now, if you write 10 equations in 10 unknowns, it takes a long time to write. So you might as well say the coefficient, will pack it up in one thing, put it in an array, in a table of coefficient, we'll call it matrix, right? The variable x1 to x,000, instead of writing x1 to x,000, you just write 1x and say it's a list of 10,000 numbers. It's fine. The right-hand side is also b, but that also has 10,000 numbers, okay? So instead of writing so many very long things, you say ax equal to b. Okay, so first thing first, we're not doing anything advanced, but we're doing it efficiently, right? Efficiently. And I did mention to you, right, that advanced in computer gaming, it comes down to this matrix multiplication, because every time you want to manipulate light ray or picture or move things in 3 dimensions, but in fact, the screen is 2 dimensions, all it is just from this point, go to that point. So it's all matrix multiplication. Good. And then I even give you a side note that advanced in computing device of graphical user, GPU, graphical processing unit, is very good at doing this linear algebra. It's so good, and it's so also part of what I use professionally in AI or machine learning, because neural network also uses a lot of matrix multiplication. Okay. You see a little bit of reason why today. And you see a little bit of reason why today. Okay, now from Friday, I only want you to remember 2 things. All right, one is how to solve for x in 3x equal to 13 in 5 steps. Yeah. Likewise, you do the same thing with matrix equation. Ax equal to b. Number 1, look at A. If multiplying by A is an action, like a poison, it's an antidote, it's an inverse. Okay? Now, when you do something like 3x equal to 13, you know that 3 has an inverse. The only thing that doesn't have an inverse is multiplying by 0. You killed it, right? Well, in matrix, the analog is not multiplying by 0, but it's multiplying by coefficient that has less information than you need. 2 equations, but actually the coefficient, the first coefficient and the second coefficient is actually multiple of one another, right? Or you have 3 sets of coefficient, but if you take 5 of the first coefficient, multiplied by, add to it, minus 7 of the second set of coefficient, get the third coefficient. So you're cheating. So there's something missing there. It's like that's the missing, that's the 0, okay? And the concept of this is called determinant. It determines whether or not the inverse of A exists. So that's step number 1, okay? Step number 2, find it. Find it, okay? How do you find it? You find something that multiplies to A and reverse it, right? So if you take poison and you take antidote, it's the same thing as drinking water. Nothing happens. Nothing happens in the matrix world is multiplying by identity matrix. Okay, so step 2, how do you find inverse? Find something. And this is where you actually spend time in maybe a 101 class. Okay, so find inverse of matrix A. Find inverse of matrix A. Now, what's the step 3? Step 3 is, well, once you got it, you just left multiply both sides, right? Multiply both sides. Run it. And then step 4, you recognize that you have something that A inverse multiplied by A and X. Instead of multiplying A to X first, you multiply A inverse to A first. And that sort of like cleans it, okay? Wipes it out. So step 5, you look to your right-hand side, there's your solution, right? There's your solution. Now, I gave you algorithmic thinking is very important part of class-6 education. So this is mathematical thinking. Find an A, multiply the left-hand side, you get the solution. In real life, it's very expensive computationally, if you have a big matrix A, to find another inverse of A and keep it. It's very expensive. Okay, it's hard to do. It's hard to do. Think of it as you need to store A in a warehouse. And if you need another warehouse space to store A inverse, you have to pay more. Okay? So what happened is, instead of multiplying the whole thing of A inverse, you have this thing called Gauss-Jordan elimination. It's a sequence. You actually multiply by something that keeps cleaning up, right? So keep making the left-hand side look more and more like identity matrix, right? So first, when you have a whole bunch of things, maybe you just make the first column of that 1 and all 0. Next step, you go to the second column, you make 0, 1, and everything else 0. Okay? And I actually prepared sort of like interactive or Mathematica play around for this. It's called play with Gaussian Jordan elimination. Gauss-Jordan, sorry, Gauss is the name of the guy, Jordan. The difference is this. Never mind, just the tiny detail. Gauss just sort of like makes it looks like everything has a 1, 1, 1, 1, 1, 1, and a whole bunch of jumps on top. Jordan actually cleans the top as well. So it becomes Gauss-Jordan elimination. So at the end of the day, so Gauss elimination is like solve for back substitution. Gauss-Jordan is like you've done the back substitution, so you end up with the solution. Okay? So with that solid understanding, you have to learn the mechanics of how do you find the inverse? What is it that performs a Gauss-Jordan? I can, we can spend time on that, but I won't, because once you got the perspective, the mechanics, I think it's something we can do with later. Okay, so you can talk to me, and you can I can give you the sort of like play assignment. Good. Now, what did I say at the end of class? Today, I'm going to start with A, X equal to B, right? But my perspective is different. Perspective on Friday is somebody gave me A, X equal to B and solve for X, right? And I even told you that in life, you will only be paid when A does not have an inverse. In other words, the determinant A is 0, and so you have infinitely many solutions. Okay, so in life, no solution, that's also part of life, right? In school, unique solution. Okay, in school, unique solution, always. Teachers always give you something that has a unique solution. Well, most of the time, okay, in grade school anyway. In life, you will actually face similar situation, two similar situations. One, no solution, can't do anything. Okay. 2, infinitely many solutions. Then you find the best solution. Find the best solution, right? Oh, I'm being inaccurate here. To be precise, in life, there's one profession. There's one profession in life where you are asked to find the solution. Anybody knows what that is? Cryptography. Cryptography. Okay. Cryptography is like you have two things multiplied, you get the right hand side. Okay, you find what are the two things. That's it. Just one solution. The problem is in cryptography, that solution is impossibly difficult to find. Okay, it's impossibly difficult to find. Okay, now I show you the graphical plot, right, of different countries going. Remember that the tour, the shortest path. Okay, well, that's also one of those things where if you define the solution, not just any kind of path, right? Any path is a solution, travel for all the cities. But if you say the path that has the shortest, okay, that's also, it may be unique, it may be not, but most, but even to find one solution, your job is done. In fact, you probably get more than a job. You get a Nobel Prize or something. Okay, few medals, mathematics. Actually, it's called Millennium Challenge. You get $1 million for that. Okay, you don't even have to solve it. You just have to solve that the class of problem for which this is not solvable and that's not solvable is the same problem. It's that difficult. Okay, so you get $1 million not for solving this problem, but just to say that this kind of problem and that kind of problem, are they equivalent or not? Okay, it's like one equation is ax equal to b, and the other one equation is cx is equal to d or something like that. And you say the solution to this problem and that solution is in the same kind of set. That's all you need to say. That's all you need to say. If you could say that, somebody will give you $1 million. It's called Millennium Prize. Okay, there are about 7 or 8 Millennium Prize, and there are about 2 or 3 left. 2 or 3 left that nobody has claimed $1 million. Anyway, okay, I digress. So, solving for x was Friday's perspective. Today's perspective is different. Today, you're given x, and you're given a, and you ask to try what's going to happen to ax. In other words, property of b given a and x. Okay. Now, before we get to the code, and I can show you the code, I'm just going to give you the perspective, and it may not make sense right now, but think of it this way. Let's imagine this room is a graph, is a plot, right? There's an x, y, and z coordinate. Yeah? Okay. And this is battery done in computer modeling. Let's say that corner right there at the bottom, that's 0, 0, 0. Okay? 0, 0, 0. So where I am is a coordinate. So you can say something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, comma, 1, 2, 3, 4, 5, 6, comma, 1, 2. So what am I? My head. What's my head? My head is a vector 10, 6, 2. Right? That's my vector. Okay. Now 2D computer graphic is actually 3D projection onto 2D. But you think of that. Think of a game, right? I'm a character in your game. Okay. Right now I'm standing at 10, 6, and 2. Right? If I'm gonna move over here, or I'm gonna shoot the gun to that direction, okay, I'm shooting my gun from this direction. Okay, what do? I add a vector. Right? I add a vector. Let's say I add a vector called, okay, I'm gonna add a vector called -5, 0, -2, -1. -5, 0, -1. Anybody? Go to the middle of the room, right? 0 means I don't move this way, and I go down 1, so I'm shooting somebody over there, right? That's called addition. That's vector addition. That's it. That's how I move from place to place. Yeah. But let's say in the computer game, I'm not shooting. Okay? I'm not doing anything. I'm standing here. The 0, 0, 0 is actually your perspective. So that's how you look at me. Now, what happens in 3D games? Do you just have a static view? No, you can move around, right? Right? So think of moving from here to there to look at me from a slightly different angle. Okay? From that angle, if that was 0, 0, 0, who am I? Anybody? -1, 6, like before, and now I'm down, -3. So somehow, from that perspective, I was a 10, 6, 2. From that perspective, I'm no longer that person. My name is now -1, 6, -2, or whatever. Okay? right? How do you think I get that original vector to this vector? How? Multiply by 3 by 3 matrix. Right? Right? Okay. Now I'm teaching you a very, abstract concept. Then you get to see how it works maybe numerically later. Okay. Actually, what do you think happens when you move from here to here? You move your perspective from here to here. How does my appearance change? Well, you want to see me from that side, you see me from this side. What else changed? I'm actually a little bit bigger, so I'm a little bit closer. Right? Okay, so remember that. Remember that. Matrix multiplication does two things. It reorients. So if you think of that, it's a direction of arrow. This becomes the direction of arrow. So the arrow change. Now, what happened in computer vision is not you moving the zero. Actually, the 0, 0 stay fixed. I'm the one who gets moved on the screen. Okay? Even though the character doesn't do anything. The character is standing still, but when you move the screen, the character moves. Okay? So actually, it's not the 0 moves, it's actually I move. Okay, but that's trivial. Okay, so do you understand now how computer graphics works? Okay, some of you might go on to be a gamer, game programmer, but okay. The difference is that with game, you have another thing coming. Because the perspective is 2D, you have to translate the 3D coordinate that's inside the computer into 2D projection. Now raise your hand. What do you think happened to do that? How do I make that happen? I multiply by another matrix. Okay? Except this matrix has 2 by 3. So a 3D projection onto a 2D plane, which is your computer screen, is nothing more than 2 by 3 matrix multiplication. Okay. Now, to get back to that problem we saw earlier about moving perspective, actually, if you're just moving perspective, you don't even have to multiply the 3 by 3 first. You actually do everything at once with the 2 by 3. Okay, and that's beside the point. Right. So think of 3 by 3 matrix as a movement in original space. This is very important, and this is where, again, I'm packing even graduate level understanding. The concept of moving between space. Okay, we are a 3-dimensional animal, but when we appear on the screen of a video, we become a 2-dimensional animal, right? But the picture still gives you the sensation of 3 dimension. But technically, once you're on screen, you are 2-dimensional. So somewhere in there, there's a 2 by 3 multiplication. 2 by 3 matrix in there somewhere. Okay. Okay. Now, before I go on, I'm going to ask you, my location makes me a 3-dimensional object, right? But is that all there is to me or you? No. So imagine that X, Y, and Z position is just 3 numbers. What if I want to add another number? Okay. Let's take a number that also has absolute 0 and negative. What if I add your height? So now you are a 4-dimensional object. What if I add your weight? Now you are a 5-dimensional object, right? Now, in data science, in big data, the biggest advancement, what makes it big data, is the fact that you can work with higher dimension. That's nothing new. Matrix algebra has been doing that for billions of years. The innovation of big data is computer will use to multiply matrix. So multi-dimension of real number line. What if one of the axes or one of the dimension is a category? What's category? Nominal scale. So imagine the first dimension is X, second dimension is Y, third dimension is Z, right? Fourth dimension is height. Fifth dimension is weight. Now, let's say the sixth dimension is not a real number line. A sixth dimension is a binary classification. Boy, girl. Right? In which case, my sixth dimension is boy. Right? I can have seven dimension. Seven dimension consists of classification. Animals, minerals, or vegetables. Right? Where do I belong? I'm not a vegetable. I'm not a mineral. I am an animal. Right? The big data revolution, one of the things that is more important than you think the word big is like huge, is the fact that we have figured out a way for computer to work with this kind of scale, multiple kind of scale, not just real number line. And that's why we start with color, shape, sound, chemical configuration, genetic information. These are all really complicated set. Okay. Right? So think about that. Think about that. That is really where you are. Again, when I was your age, I would have gotten a straight A just to be able to work with matrix of high dimension, all real number. Nobody ever bothered to ask me, what is it like to have 7 number as a boy versus girl? That wasn't part of my world. Okay? Because yes, there's a boy and a girl definition, but you didn't calculate anything with it. You didn't do much with it. Okay? You didn't take a picture and do a object recognition and say, this is a girl, this is a cat, this is a dog. That wasn't part of my world. Okay? But something numerical, height, weight of a cat, fine, no problem. I can stick that in. Okay. So what happened is the dimension gets generalized. Okay. Now, I'm going to keep saying all the advanced stuff in a baby language. Hopefully, if you retain this, 2 years' time, you will get higher insight from this. Even words can now be put on a coordinate. Okay? The reason you have ChatGPT, okay, today, and you didn't have it 10 years ago, okay, is because computationally, nobody was able to put English or Thai words on a numerical coordinate. Now, I want you to actually be alert. This is going to require a lot of mental gymnastics. Remember I told you about the error of taking nominal scale and doing, say, addition, multiplication, subtraction to it? Okay, that's bad. That's bad. In general, that's bad. I would tell you this. This is the secret of ChatGPT and any natural language programming. The reason it's so powerful is because somehow the computer has been big enough with certain algorithm to turn words into multi-dimensional vector that belongs to an interval scale. Okay? Now, if you're smart, you should be getting a goosebump right now. Why? Because now you can do addition and subtraction with words. Right? If you use ChatGPT, well, I'm going to do even more basic than that. I'm going to do addition and subtraction with words. Okay? See if this works. Queen minus girl plus boy equal king. Right? So now you have literally nominal scale object words that you can do addition and subtraction with. But you do it the right way. Okay, you're doing it in a completely legit way. It's a concept addition, concept subtraction. Okay. Likewise, I can say hot multiplied by very, and I'm with very hot. Okay. I can take hot minus cold. I can take very hot minus very cold. Okay. And ultimately, when you go to ChatGPT, you can say, what happens to a human body when you jump from hot shower to cold shower? Okay? And it will understand that. If you say, what happened to human body if you take it from extreme heat, like in a sauna, to extreme cold, like in an ice bath? It will also understand that. Because in the mind of ChatGPT, there's actually an inferred distance between hot shower and cold shower, and sauna and ice bath. Right? So I'm going to leave you with that, because if you can actually understand the mechanics of this and how it works and code it and do something with it as an application, you're pretty much at your senior year Basai in applied digital intelligence. Okay, that if you everything I said today just now, if you know the mechanics of how it literally works algorithmically, you can code it, you can program, you can take data, you can experiment, you can fine tune the model. You're pretty much a senior right now in data applied digital intelligence. Okay, but obviously you're not there yet, so that's okay. You have 4 years to get there. Okay, so right. Now let's get to the subject of today, right? Well, I already started the subject of today. What happened to a vector when you multiply it by a matrix? Now I'm going to keep to the same space. So if it's 3, it's 3. Okay, so multiplying by square matrix. Okay, so I'm not doing it. By the way, if you go like internet, you can see they do word projection. In other words, this thing about king, queen, and hot, very hot. A big cat is equal to a tiger or something like that. A cat multiplied by huge and man eating or whatever. Okay. When they display this, they have to display this on a plot, right? 2D plot. So somewhere in there, there is a 2 by whatever dimension it takes to represent word. Now, I'll give you a magic number. Okay, this is what data scientists and AI researchers work with. Every word in English, you have to represent it in coordinate. If you make it a 2 coordinate, it's too small. How many is enough? Well, then it turns out the practical number that we've been working with, in the future this may change, is 300. So every word in English maps into a 300-dimensional vector of real number. But that real number, even though it has positive value, negative value, there's no absolute. Okay, there's no absolute. So it's actually an interval number, interval scale number. Okay, so that's called word embedding. You embed cat into 300-dimensional space. You embed student, boy, girl, difficult, easy, hot, cold, all the million words in English and also in Thai in 300-dimensional language. Now, I didn't care much about NLP research in Thailand because it takes a lot of money and computational hours, literally, to run algorithm to do this in a sensible way. In other words, in a way that you can say queen minus girl plus boy equal to king. Okay, that is a very difficult, expensive exercise. Google did it obviously many years ago. Okay, algorithm for doing that exists, but I don't have the computational power. Chulalongkorn doesn't have, it didn't invest in this. There's an institution called Vistech. Vistech wants to do this and they got money. Okay, I know because I was with SCB, we gave lots of money, and also PTTEP, exploration and production. They have lots of money and they focus on this. So what they did is they bought really big game cards, expensive game card. Now, your expensive game card is about 100,000 baht, right? 100,000 baht. Well, their card is about 2 million. Okay, and even with that, they tried this exercise. They did more, but this kind of language embedding for Thai language. And I think it took them like 8 months of computer time. So 2 million's worth of computer running for like 8 months. Now, they didn't just do this embedding, they did more than that. But certainly, the point is that once they've done it, it becomes well, because Vistech is not a company, it's a university. It becomes a public property, right? So now you can say, you can use word arithmetic in Thai using this thing, because once it's computed, they store the value. Now it's easy to store value, very easy, okay? So let's say we have 2 million words that's embedded in the Thai language. You only need 2 millions by 300 numbers. That's very cheap. And so that can be put in here. So now you have AI in Thai language that 10 years ago you couldn't. Okay, well, 10 years ago, even 10 million baht worth of computer wouldn't do it. So the computer also, so you're actually born at the right time, I guess, right? It's one of those things, if you're born at the end of World War II, there's a convergence of something, technology and prosperity and peace. Well, here, you're actually born at a time of another convergence. Okay, a lot of things that I envisioned when I was your age was just like a dream. It's not doable. Okay, I had brilliant idea, but just that. Okay, you can have pretty good idea and make it happen for free. Because this Thai language is already there. Okay. So I tell you what, it's sort of like just make it a nice break, because when we come back, we'll do the computation. Okay. So why don't we take an early break? Okay. And then when we come back, we go into the notebook mode. Okay. So that's an early break. Sorry. I'll make it nice transition. Yeah. You want to pause first? Okay,ครับ. So welcome to the second half of the sixth class, right? Okay. So before the break, right, I talked about the concept already. And the concept of linear algebra and space and the coordinate is so powerful that, again, even in these days of large language models, you really can't get beyond, multi-dimensional vector, right? Okay. So just this should motivate your attention in something that seems as mundane as linear algebra. Okay, the fact that a cat is actually a 300-dimensional vector, so it's a dog, and you can do something like add, multiply, right? Cat multiply by ferocious, get to something like wildcat or lion, tiger, whatever. Okay, good. Now let's get concrete. Again, I want you to pretend that I am you today at home. Okay, today, let's say today I from the first before the break, you learn about matrix multiplication, and I told you about this thing where you have a vector in 3 dimensions, you multiply by 3 by 3 matrix. What does it do? It changes the direction. It also makes it longer or shorter, whatever. Okay, and that's it. Let's say you went home. You went home. Okay, right now you're at home. You're by yourself. Okay, you want to explore this concept. So let's try to do that. Okay, so let's make the concept real, but I'll make it in 2 dimensions just to make life a little bit simpler. Okay, so let's say where was my position? My position was x. Okay, x is equal to 10 and 6, right? Ten and 6. Okay, my position was 10 and 6, and now I'm going to multiply and move. So I actually don't know where I'm going to end up. So just make up something. Just make up something. So this is my x. It's my x, right? Okay, let's make it large. Sorry. Yeah, so that's where my starting point is, right? I'm a 2-dimensional object. I start at 10, 6. Now I'm going to start moving this thing. Gonna start moving. Now remember, this thing is reference to 0 and 0. Okay, so if you think about it, you done Pythagorean theorem, right? How long is this thing? 10 square plus 6 square, square root, right? Right? Now, I'll give you a word for it. The word is norm. Okay? Now, if you go to the language helps, okay. Language help, and you go to norm. Okay? You can see that I can put in norm and it gives you the size, right? So let's okay, this is more Pythagorean theorem, right? You guys memorize this when you were young, all right? 3 square plus 4 square, square root of that is 5, okay? So that makes sense, right? So this norm, what does it do, actually? What's norm x? Norm x is the same thing as x1, right? Square, okay? Plus x2, control hat, square, and square root. Is it equal to that? Let's see if it's equal to that. True. Okay. So norm gives you the size of the vector according to Pythagoras. Okay. That is actually called Pythagorean norm, or technically 2 norm. Why is it 2 norm? Why is it 2 norm? Okay, I'll tell you. Let me go to palette and write something more fancy. Math assistant. And I write this formula. Okay, I use this. Can you guys see that? Right? I don't remember the shorthand for this, so I go to the palette. But let's do this again. There. And put 2. Right? So basically, the first value square plus second value square. So 3 square plus 4 square is equal to 25. Take the square root of that. That gives you 5, right? Does that make sense? Okay. Now, here's the thing. Here's the thing. This thing is Pythagorean norm. It's called 2 norm, right? But if you think about it, I can also do this. Okay? Dimensionally, it would still work. Think of it as centimeter. Centimeter to the power 4 plus centimeter to the power 4. And you still get centimeter to the power 4. You take the 4th root of that, you get back centimeter. Dimension works. Okay? This is now called a 4 norm. This will be slightly different. Okay? Be slightly different. Okay? Be slightly different. Okay? Likewise, now, you can put odd number here as well. The problem is when you put odd number, it go negative, right? So what you have to do is you have to make an absolute. Right? Absolute value. Huh? Okay. I want to hear some clicking sound. You should be clicking this. Okay. Now you are a very good student. So even before you work, go to that, you're exploring something else, right? Okay. So now, does this work? It's working. Okay. Now you want to make your life interactive. What do? You take this. Hey, wait a minute. Ajahn Pumjai said, you can do 2 norm, 4 norm. I'm going to get fancy. I'm going to make K norm. Okay. I'm going to make K norm and I'm going to manipulate. Right? And interactive mathematics, guys. It means nothing if you don't use it. This is very expensive software. So how about start at 1? 1 to 10 instead of 1. Oops. Right. Now, let's make it 20. Okay. I'm going to give you something cosmetic, but control type. Slider. Okay. And control placement. Control basically means a knob. Right. Okay. So that's all. Okay. Now, so right now, when K is 1, okay, what's the length of this vector? Remember, this is what? 3 and 4, right? Your thing is not cooperating with me for some reason. Please, what does it say? Please move this window away from share. Oh, for some reason, when I do this share, it doesn't like it. Okay, anyway, let's do this. Let's make it from, instead of doing this, let's say, let me try again. Let me try again. Ah, it works. Okay. Okay, and so on. Now, this is going what? K from 1 to 10 instead of 1, right? Now, I'm going to try something else. Well, first of all, let me make it, let me add n to it, so it gives you a number. Okay, so 7, and as you move higher, it gets smaller. It gets closer to number 4. I'm thinking something is funny. Let's try something. What if I want to go from 1 to infinity? Can I do that? Well, you can't do this in infinity, so you can list it. Okay. So instead of going from 1 to 10, instead of 1, I'm actually going to list the set of things I'm going to try. And it's not going to be a slider, it's going to be value. So 1, 2, 5, and the last guy is infinity. Okay. I have to put another bracket. Okay. 1. Okay. So 3 absolute value plus 4 absolute value is 5. 2, that's Pythagorean, right? So when I click 2, that should be Pythagorean, right? 5. Okay. 5 gets smaller. Infinity. What is it going to get? Oh, okay. Because this is a calculation with an n. Yeah, I cheated a little bit. What I want to do is show you this concept. So let's make it not infinity. Let's make it a large number. Forgot. Yeah, let's make it large number. Okay, this is the lesson. As the norm goes up, it gets closer to the largest number. So this is the same thing as a max. Now, why do I say this? Because now this is the inside way of doing it, right? But this is called creating the norm. So when you go to this explanation page, you will see that here, that's the power of the norm. I use K, but it's they use P. So let's make it P. Sorry, power. Okay, so let's make it P. Now, I don't want to do this with my own formula because for a large number, it doesn't convert. So I'm going to give Mathematica its own vocabulary again, because if I want to Mathematica to do things symbolically, I have to let it do symbolic things. So norm of x to the power p now works. Okay, works like before, except now I can put infinity. Okay, because again, infinity is symbolic thing, right? I was writing it out myself, so it didn't take that symbolically. So now it takes it symbolically. Okay, this is what's called infinity norm. Okay, now there's only 3 norms that you need to work in real life. 1 norm, 2 norm, infinity norm. Okay, why is that? Why is that? Because it has a real meaning. Okay, I'm going to write down 3 words. I'm going to write down the words Manhattan and helicopter and infinity. Okay. Okay. You standing at the corner of 5th Avenue and 11th Street. Okay? 11th Street. Okay? Your friend lives 3 blocks east. Okay? Have this in your mind. 3 blocks east, 4 blocks north. How far is your friend away from you? Well, that depends. How rich are you? If you are rich, you have helicopter on top of your penthouse apartment, right? You fly to your friend, right? 3, 4 is 5. So 2 norm is a helicopter norm. It's the distance from the origin to the tip of the vector if you take a helicopter ride. Okay? Okay, let's come back to Earth. You're just a student or anybody else who's not super rich. You don't have a helicopter. You have to walk to your friend. How far away is your friend? Let's say each block is 100 meters. Your friend is actually 700 meters away. Because it doesn't matter which path you take, you can't cut across building, right? So you have to go that sort of like this. So the absolute distance in x direction plus the absolute distance in y direction. That's your thing. Right? That's your thing. Okay. Now, if you want to decide which way is longer, the x direction or the y direction, take the maximum. And that is the infinity norm. Okay. So infinity norm is the same thing as max. Okay. Now, this is sidetrack, right? This is sort of like you come home, you were going to play with the vector, and you thought of Pythagorean theorem, and you thought, hey, wait a minute. If I have an original vector, I should be able to play with Pythagorean. Maybe I go search around, say, oh, Pythagorean is called a norm. Look up the norm function, you play with it. So you wasted already half an hour on your own. But that's learning. Okay? This is you on your own now. This is you in your apartment. Okay, so let's go back to the lesson we were learning today, right? So I have x. By the way, you can spend another 15 minutes changing the a and b, right? So that makes life easier. So let's do that. So we have, well, let's not do that. Let's say x. Okay, now, I'm going to get a involved. A is equal to, say, I don't know, minus 5, minus 3, plus 3, comma, 7.2 plus 0.9. Oh, I don't know, something like that. Okay, just for fun. Okay, just for fun. Maybe I just this is completely nonsense. I don't know what this is going to do. Okay. Now, I'm going to do this. A dot x. By the way, again, Mathematica, you just use space, right? But for this case, because it's a matrix multiplication, you use dot. That's the only thing you have to memorize. Okay, so that's that. I start at 3, 4. I multiply by some matrix I just came up with, and I go to minus 7 plus 36. Okay, let's make it a little smaller number. So right. Now, I want to show what the line looks like. So how do I do this? Line, list, You know list plot already, right? List plot, we just take point and this point. But what if I want to draw the line between them? I use list line plot. Okay. Now, list line plot obviously cannot take a point, right? So now it's going to take a set of points. Okay. So let's draw a set of points from origin. What's origin? 0 and 0, right? So this is 0 and 0. Okay. And draw this to x. What's my x? Oh, sorry. Ah, there it is. Okay. 1, 2, 3, 1, 2, 3, 4. Okay, let me make it smaller. Plots. Let me add cosmetic touch. Plot size small. Oop, not plot size, size plot. Huh, don't remember. For some reason, it does. Oh, sorry. Image size. Okay. Again, even I have to go to help. Image size small. So, okay, so that's the first line, right? What if I want to make a second line? Now, I can't keep adding to this because this is one line, right? So what I want to do is I want to put another line. Now, list line plot is smart enough to say if you give you a list of beginning and end, it's going to treat them as separate line, right? So this is the first line, right? So this is the first line. Okay, this is the first line. Okay. Now, let's make it a set of line or a list of line. And then I can do this. Instead of plotting just A, I plot AX. I see that? Right? Right? AX. Okay. Now, how would you do this for real? How would you do this for real? I mean, how would you learn, right? This, you just have one set of values. So that's no good, right? So what would you like to do? You'd like to see what happened when I changed in different values, right? So why don't I do this? Why don't I do this? Instead of doing like this is kind of like not so nice. I'm going to do this. Manipulate. Okay? Manipulate. Okay? Manipulate. Now, what can I manipulate? I can manipulate one value at a time, right? So what I can do is this. What I can do is this. X1 from, I don't know, 3 to 4, and 3 to 1 to 10, okay? And then X2 from 1 to 10. Okay? That's what I want to do. Okay? That's what I do. Now, X1 and X2 would have to go into the value of X, right? Okay? So, let's do this. X is equal to x1 and x2. Okay, so now, even though x was original 3, 4, now it gets a new start. It gets a new start. Okay, let me do control placement bottom. That's better. So get out of the way. Okay. So now if I move x, notice x is 1, 1, right? Now, the reason it doesn't have 45 degrees because it automatically scale. You can fix the scale, but you know, it's trying to make it look nice. So what happens when I move x1? I can make it higher. I can make x2 higher. Actually, to be honest, we can start at minus, right? Now, here's the thing. Here's the thing. Minus 10 to 10. Okay, minus 10 to 10. Okay, so it's going to start from minus 10 to 10. Right? And this is something I want you to remember. Because occasionally, again, think of pitching this project to your client. X can change from minus 10 to 10 depending on your client's sense of beauty. Okay. Okay. So your client can, let's say this is a design object and you know, this looks nice, this doesn't look nice, your client can play. But let's say you have a favorite design. You want this display to start with a particular value. You can do that. Okay. So it's not the default value, it's called starting value. Okay. How do you do that? Well, you want to start the value close to the variable you start with. So let's say your perfect concept of a beautiful vector is 3, 4, right? So I want to start x1 at 3. This is what I do. I put x1 in a bracket. Oops, sorry. In the bracket, comma 3. Okay. When you search, this fall under initialization. Okay, but I'm just giving you this because it's so easy to remember. So how about this? Let's do this. x2, comma 4. Now, you can still go from minus 10 to plus 10, but it's going to start at 3 and 4. So that's a beauty. That's a beauty matrix, right? That's kind of like original thing. So see that? So if this is your original vector, this is your moved vector. But we don't use the word move because that's kind of baby. We use the word transform. Why is it transform? Brother, how is it transform? Come on. If this were a pop quiz, you would say it's transformed in 2 ways. The direction and the length. Okay? Or if you want to be perfect, direction, extension. Okay? Direction, extension. Okay? So that's the perfect, that's a okay. Now, you guys remember this? This A here. Okay, let's write it down here. Now, this is nice, right? This is nice. I'm going to give this to you as a copy so you can use this as a template. It would be nice, right? If you don't have this X going around outside. So likewise, you can do something like this. So this is more fun, right? So this is something like put in the A's, X and A. Now, if I did this, that means I have X global. Remember, there's a way to hide this. It's called module, right? So what I do here is, first of all, let me clear X. Okay. Now I wrap this under module. And what are the things I'm going to write? Module is, that's my module. X is equal to this. And notice all the ray comes up, so something is not right. Well, it's missing a bracket. So now it's nice. Yeah, can you see that? So now it's nice. Okay, and let's make it to the right. Okay. Likewise. Okay, let's play some more. Let's play some more. Okay, I'll give you to this. Let's say we also want to play with something else. What else do you want to play with? A, right? Now, again, the knob can only change one value at a time. There's advanced knob that changes two values at a time, but I'm not going to do that, okay? But it's going to make it look nicer than this. But right now, just say A11, A12, right? And then what? A31, and there's A32. Okay? Now, what I'm going to do is I'm going to initialize it in a very boring way. Okay? I'm going to initialize it in a very boring way. How do I make a matrix boring? Anybody? Identity matrix, very boring. Okay? So 1, 0, and then 0, and then 1. Okay? And now I'm going to add A to it. And I'm going to say A. Okay? So you turn in your sort of like worksheet to show your work. And after you turn it tonight, tomorrow your TA will give you this. So you can play some more. Okay? And you can play with 3 dimensions. Okay, so A11, A11, A12, A121, A22. Okay? And separate by comma. Now, it's worth pausing a little bit. Okay? So this is a basic setup, by the way. You will use this for 4 years. Manipulate outside, controls everything, right? Module inside hides the detail, all the dirty works that you have. So now it doesn't affect anybody because A is now in green. Okay? And then you have to manipulate. Sorry, it should be 2, 1, 2, 2, not 3, 1, 2. 2. Okay? Right? Define the module. Define the module. What are the things that you want to define locally? A and X. What do you want to do with it? Yeah, I want to do this with it. Okay. Now, if it's one line, I can actually stick this in here. Yeah. But, well, I might as well do that. So you see that there are 2 styles of doing things. Okay. You can do this as well. Because it's so simple. You can do this. Okay. But normally, you don't just assign it once. You do something to it in many steps. So you do it below. But let's have something like this. Simple. Okay. And what's the action? I want to plot X first. And then what happened to X when you apply A? Okay. And let's make it another thing. Size image is equal to small, medium, large. Okay? Small, medium, and large. And this also becomes size image. Okay? So now, of course, you can make medium, large, but I'm going to keep it small, right? Notice what happened. This is really boring, right? This is boring. Why? Because this thing, A1, 1 is 1, 1, 0, 0, 1. That's a linear. That's an identity matrix. So it does nothing. So the blue line and the yellow line is on top of one another. Okay. Now let's do something interesting. How about if I can move this, okay. By the way, by using the slider, if you want to see the value, you can click right over here and it's going to allow you to enter manually. Okay, I don't use this often because I don't necessarily need manual value. But let's say in this case, I want manual value. Anybody see what happened here? What's my A matrix? It's -1, 0, 0, -1. So it's identity matrix with a minus sign to it. So it's saying do nothing, but turn everything upside down. See that? So from 3 to 4 becomes -3, -4. Okay? -3, -4. Okay? Now, I'll show you something that you should be interested in finding out. Hey, this matrix is good, right? Because if you think about it, the blue line, okay, you can draw this line infinitely, right? And the blue line and the yellow line, right? Well, that's like what I was talking to you about earlier, like intersection. So maybe we can try what happened when the top line is a combination of the second line, or the top line and the second line are the same. So let's see what happened. Well, we can do this. How about this A11, A12, A21, right? So instead of -1, 0, 0, -1, let's make it the same. Oops. Now, in this case, gives you something else. Okay. Again, this is because you're playing thing, you don't have the right-hand side. If you start to have A and X and the right-hand side, then X, the two lines would have big trouble. So yeah, it's okay. In this case, no problem. So you can play with it all you like. So you play with it all you like. So let's start with something more interesting. Tell you what, let's do this. Let's random real so that it gives you something fun to play with. Okay, so every time you enter, it's going to give you a different thing. Okay, now let's make it more interesting. Let's make 1 minus something like that. I don't know. Okay, right? So all this, now obviously it has a starting value here, so you can read what the value is actually, right? So you can take this and do by hand multiplication to see if it gets what you want. Okay, now, like I promised, we're not trying to solve for x. We're trying to see what happened to x when you multiply by a. Notice this, okay? What if the two things you can change, you can transform two ways, change direction and the extent. And by the way, flipping upside down is also extent, right? It make everything negative. It's also extent. Those are two things. Change the direction, change the extent, change the size. What if you want to do one or the other? Can you do that? Yes, you can. Yes, you can. Certainly, you can take the vector and make it longer or shorter in the same direction. Or you can change the direction, but keep it the same size. Okay? In a way, it's sort of like, I'll just give it to you right now. You multiply by a that has a determinant of 1. That determinant is not only whether or not you can find the inverse. It's also sort of like the size. Okay, so when you multiply something by a matrix, that matrix, the determinant of that matrix is kind of like a size multiplier. So if I give you a matrix that has determinant of 1, identity matrix, for example, right? This is the size of 1. that matrix would not make it longer. And you saw that, right? It just flip it upside down. Okay. So it doesn't make it longer, but it can, basically just make it circle. That's not the interesting one. The interesting case that I want to talk about, okay, for the rest of the class is what if you don't want to change the direction? You change the extent. Okay, that sounds like, hey, I gave you something powerful, that right? And now I'm going to restrict it, make it really stupid, do nothing, make it do nothing but just longer and shorter. Why would I do that? That sounds stupid. Okay, hang on. There's a reason why. Okay, now how is that achieved? Well, I'll just give you the answer. You multiply, like we saw before, by something that looks like an identity matrix, but the coefficient can be different. So let me do this. Yeah. Okay, let me do this. Okay, I'll give this view again later, but I'm going to give another one. Again, this is a stupid one. Okay, this one, I don't allow A and A1, 2 and A2, 1 to be anything. I take this away. Take this away. Okay, so this is actually 0. I make it 0. Okay, worse. I'm going to make it worse. I'm going to make A1 and A2 the same value. So A1 and A2 is exactly the same thing. Okay, so this is a lot more boring than before. It's a lot more boring. Okay, does this work now? Yeah, of course. See that? Okay, so what happened is it doesn't change the direction, it just changed the extent. Now let's do this manually. I can make it longer. Unfortunately, when it's longer, it just blocks it, right? Because of the, so, okay, this is the negative. So the negative one, you can see. The positive one is just kind of, right? See that? So now it's half. So think about it. Look at this. This is 0.5. Okay, oops. 0.5. Okay. Right. Oops. Oh, okay. I make A random. Sorry. Let's start at boring. Let's start at boring, and let's change it manually to 0.5. Okay. Notice. Oops. I don't know why it's giving 2 copy. I'll just delete one. Okay. Right. Because A is equal to 0.5, all you're multiplying is 0.500, 0.5. So even though you have 4 places to put number, you only put in 1 number. That is kind of silly, right? That's not using the full capability of a matrix. Because if you think about it, it's just a scalar multiplication, right? So when I make this restriction that the diagonal only and the value is the same, multiplying by matrix is the same thing as multiplying by 0.5. Okay? So it's the same. It doesn't do anything. So what this means is that, okay, now if this were, I'm going to put, instead of line plot, I'm going to put something else. I'm going to put true or false. A dot x equal to A times x. Okay, this is what I want to show, right? The left-hand side is a matrix multiplication. The right-hand side is a scalar multiplication, right? So you have A1, A2, A21, A22 multiplied by X1, X2. And the other thing, you just have X1, X2 and multiply by number A. Is it the same? Oops. Why is it not the same? Hold on. It should be the same. Hold on. Let me just list them. Wait, oh, I forgot to clear. And now it's a X. Now, because I don't have a definition anymore, I have to say something. Yeah. I haven't cleared A. Either. Yeah, that should be okay now. Tell you what, let's just list everything. Just list A and X and see what happened. Yeah, this is why it's up. It doesn't have to value. Oh, sorry, my bad, guys. I put AX over here. AX should be inside the module, right? Because after all, that's what I want. Okay, so this is what I want. Okay. Whew. Okay, so this is my A, this is my X, right? So if I ask the same question, is A dot X equal to A X? It should say true. Okay. You know the mistake I did there? I was using AX inside the module, but the module bracket is over here. I put it outside. Sorry, my bad. Okay, you get this. Okay. Anyway, so this thing here is the same. Okay. Anybody took German in high school? The word German for same is eigen. Okay, eigen. So multiplying a matrix by X gets the same thing, essentially, just bigger or longer or shorter. So the word for eigen means this thing. A times X is the same thing as X, just a bit longer and shorter. This is a special case. This is a special case. This is called eigen. I give you the word. Eigen means the same. Vector. Okay. Right. This X is an eigenvector. And for some reason, they don't call the eigenmatrix. I'll tell you why later. Okay. So this thing is called, let me put in bracket here. In this case, okay, X, where is X? Okay. So I put a comment I can put anywhere. So X is called eigenvector. Okay, actually one word. So no capital. Eigenvector. Okay, and then Y, sorry, A is called eigenvalue. Okay, so and the whole thing system, the whole thing is called A dot X is equal to A X is called eigensystem. Okay, three words. So 3 words. Eigen means same. Okay. Now, you have to ask yourself or ask me, who cares? Right? Right? I just said that X is a vector. A times X, change the direction and the size, right? That's very powerful. You can use it in computer graphic and everything. So why would I want to handicap the vector, which is 4 number in this case, to just 1 number? Why would I do that? Okay, come close, come very close, but you get the concept first, right? That it's eigensystem because when this matrix multiplied by this vector, it's the same thing as stretching or shrinking or flipping it upside down. It doesn't change direction. It doesn't change direction. It's sort of like it's a happy place. It's a happy direction. So instead of changing perspective, all you can do is zoom in, zoom out. Because you like this perspective so much. You don't want to change the perspective. You don't want to change the angle. You just want to zoom in, zoom out. Okay? That's it. That's all you want to do. Well, the concept here, once you understand it, this is how we use it. Instead of starting with an X and make A such that this turns into eigensystem, okay? That you have to handicap A. You have to make all the diagonal element go to 0 and everything just some number. Now, the opposite happened. Give me any A. A is a transformation. Find the X such that X finds A to be a happy place. Okay? Let me say that again, right? Let me say that again. X undergoes transformation, change direction, change the size. Right? Right? But think of a perfect parent-child relationship. That doesn't happen. My child is perfect. The only thing I want to transform my child is to make him or her bigger, stronger, smarter, nicer. Right? So it's that kind of direction. So no change in direction whatsoever. Okay? In analysis, this is called eigensystem or eigenanalysis, eigensystem analysis. Okay? Why is this important? Okay, I'll give you an example that probably means nothing to you because you're not an engineer, but let's say you have a friend who's an engineer. This is the direction of resonance. When you give it something and it just keeps making it bigger, it's the same thing as when I put the microphone to the speaker. It has a positive feedback forever. That's why you get this, you know, because the sound of this goes to the speaker, the sound of the speaker comes here. It doesn't change anything. It just magnifies again and again and again and again 1,000 times. Okay? So in that case, you don't want. Resonance for engineer usually is bad. Okay? What else is bad for engineers? Resonance. Frequency. You know the bridge? The bridge? The bridge is a long thing. It's not rigid. It's not rigid. So if you think of a bridge as a guitar string, you can actually plug the bridge, suspension bridge, right? Plug it, and it's going to vibrate. Okay? Well, the guitar has the frequency determined by the length. So does the bridge. If the wind pushes the bridge at that frequency, now wind sometimes just comes in big one time, but sometimes it comes in kind of wave, doing, like pushing the swing, right? That's it. If you push at the right frequency, the same frequency as the swing, your brother or your sister go wee because it gets bigger. Well, if the wind does that to a bridge, same frequency, eigensystem. It's going to get so big, at some point, the bridge is going to break. And you can get a video on YouTube for, you know, how bridge falls like the tornado or whatever. Okay, it's a long story. Anyway, so that's not so much fun. That sounds really sad. Resonance sounds like a bad thing, right? But certain things are good. Okay. Now, let me show you first how things work in life. Of course, this is done so often that it's now programmed. So let's say my A, okay, I'm going to make my own matrix, okay? My real matrix, my matrix is equal to, again, let's something, just make up something. Okay, that's my matrix, right? Now, if this matrix, you multiply this to any vector, is it going to do the same thing that matrix trick? No, it's not. Chances are it's not, right? Because you don't have this diagonal matrix looking thing, right? But this is what you do. Eigen system. Put in my matrix. Okay? Unfortunately, you get complex number. You don't know about complex number. Complex number are completely legit. Okay, but let's do this. Okay, I just make up some number that doesn't look like a matrix. So that doesn't have an imaginary number. Okay, this is it. Okay, this is it. Let's make it 0.1. Okay, so it gives that's okay. Right. Okay. What happened when, okay, and you can go to look up eigensystem. What's going to happen is that this is your A. You give it to eigensystem, and what it's going to give you are the eigenvalues and the eigenvectors. Oh, wait a minute. So, again, if your matrix is really simple, idiotic, has nothing on the diagonal and it just has a number, you can multiply it to anything and you get the same thing. So you get universal eigensystem. Multiply any vector and you're just going to shrink or expand. But if your matrix is significant, meaning it has value of diagonal and so forth, it turns out that you will find exactly two directions that is a happy direction. This is mathematics, guys. Just take my word for it because, you know, need mathematics for this, matrix theory. If the matrix is 3 by 3, you will find 3 happy directions. And again, happy direction means in that vector, if you multiply by A, it's just going to stay in the same direction. It may get bigger, it may get smaller, it may go upside down, but it's never going to waver. Right? So my perfect child gets bigger, and maybe at some point he gets older and he shrinks and he dies. Okay, fine. But he doesn't change. His personality is perfect. Something like that. Okay? That doesn't work. So a lot of times in marketing, in social media, and I'm going to finish with that application. It's the opposite of engineers. Engineers don't usually like resonance. They kind of like, oh no, I get hit with resonance. Something is going to go crazy. Okay. But for marketing or, you know, analysts, they like this. It's sort of like a happy direction. It's like, oh, I've got it. My client, man, I keep selling stuff because he likes my thing. He likes my things. All right. He's going to stay with me. He's going to stay with me. He's going to keep buying my products. So in marketing, in innovation, a lot of times you like this kind of sameness. I'll give you one example and I'll finish with that. Okay. Let's say, and this is something that you have done called social network analysis. Okay. Well, let's put it this way. Let's have all of you students or people, okay? Again, just go by 1, 2, 3, 4, 5, 6, 7, 8, up to 100. So your popularity is a number. Let's say the popularity. Okay? The popularity. if. So popularity score is called V1, V2, V3, V2, V100. Okay? Your popularity depends on how many people like you. So if you think of your vector over here representing you, so let's say you're the third guy, so it's 0, 0, 1, 0, 0, 0, 0, right? Okay. And then you have a matrix. Let's say this matrix has got all 0. Okay. And for some reason, the third column has a whole bunch of numbers. When you multiply, you're going to keep, right? So it's a little bit like that. It's like your friend likes you, put 1 in your column. Okay. Now, what's more important? If you're liked by a lot of people, that's great, right? But if you're liked by a lot of people who are not that popular themselves, versus you're liked by one guy who is popular, sometimes the second case wins, right? So it's not just how many people like you, how many popular people like you. So your popularity depends on this matrix multiplied by the popularity vector of your friends. What's going to happen? When you write this out, it's going to look like A vector equal to multiplier vector. Social network analysis. I can use Facebook as an example. Okay, so linking is considered like friend. I can take the network of Facebook friendship, call that a matrix, solve for the eigenvector, right? Now, if there are 1,000 friends, there's going to be 1,000 eigenvectors. The theory is saying take the one that has the highest absolute eigenvalue. The vector corresponding to that is how popular you are. This was done again very nowadays. It's called centrality of a social network. I can claim, okay, and I can challenge anybody to challenge. I can say that I was the first person to use this in Thailand. I'm very sure of that. Except I couldn't care less about social network. So when I used this before Facebook was such a big thing. I used this not on who's friend with whom. I use this for which bank lends money to which financial institution. Okay, so that's why I'm quite, to be honest, I'm quite proud of it because I have this. Literally, I have this document that I just dug up just for fun the other day to prove that. When was this? This was. Yeah. So this was 2004. Okay, this was before social network analysis was a thing. This is what I proposed. Now I didn't develop this immediately because there was a whole bunch of other things to work on. But this is a concept of using banks to and you know what I use for proof of concept? It's really funny because back then bank data is very private, so I can't just take it down. So it's a big approval process to get hidden data. And in fact, I didn't work on real data until almost 10 years later. But anyway, here's a fun thing. You know what I did as a proof of concept? I looked at Premier League. You guys play football or watch football? Right. How do you know which team is the strongest team? How? How do you know which team is the strongest team? It's the one that won premiership, right? Not necessarily. You can win a lot because you racked up a lot of win points against weak opponents. So remember, how popular you are depends on how many popular people like you. Remember that statement? How strong you are as a football team depends on how many other strong teams you beat. So what I did was I created a win table of Premier League and I solved eigensystem. Based on that, I get a better prediction of who was the more capable team. Because, you know, you can win premiership because you win against weak team. And next year, what happens when you don't win against weak team? So the best thing to do is, for example, you don't just play Premier League, you're going to play UEFA Cup. There, you're going to meet strong team, right? It's not a round robin team. Okay, with Premier League, you meet everyone. So it's a round robin, you meet weak team. But when you're talking about, you know, European Cup or something, you're meeting strong team. So your estimate is not historical wins, but historical wins against winners. So the best predictor I did was actually Premier League. Okay, so that's a Premier League table, win table. So I downloaded the Premier League win table and did this. Okay. Now, this concept, the mathematics, I didn't invent. I didn't invent the mathematics. I certainly could claim that I was innovative or inventive in applying it to this banking problem. You know who else is inventive or innovative at applying the same mathematics? The co-founder of Google. You know how Aaron and Page did this? It's called page rank algorithm. And it's based on this eigenvector system. You know how he does it? How they did it? Well, because they did a web crawler, so the web, just like in Facebook, you have friends that are friends. Web page has pages that are linked to one another. So which page is significant? Is the page that is linked to a lot. But that's not enough. That's like you're popular because a lot of people like you. Okay? Get it. You're popular because a lot of popular people like you. You are a strong football team because you beat a lot of strong football. You are a significant web page if you are linked to by a lot of significant link page. So there's a link matrix and there's a significant matrix. And well, he didn't use Mathematica, he used a C library or something. He solved for this relative importance of web page. This is how Google beat everybody. When internet started, Google was not the first search engine. When I was a PhD student, I used Alta Vista. And then Navigator came in. And Google started coming in. The reason Google beats everybody is because when it reaches out to get 100 web pages, it lists them in order of significance. So that's why people like Google better. Because for the same keyword, I'm not getting some obscure page that nobody cares about. I'm getting popular page that people cares about because it's linked by other popular page. And within space of a year or two, I think maybe 2 years at most, Google beats everybody. Okay. Likewise, for my case was a secret thing. I couldn't commercialize it because this used private data. This is the way we monitor systemic importance of banks in Thailand. So we don't say which bank is big. That certainly is important. But which bank lends to big or important bank? So with respect to lending, you are important if you are lending a lot to other people who are also significant in terms of lending. So I use that for the Bank of Thailand. And but obviously that's not a commercial thing, right? But you can see that mathematics Okay, Aaron Page, Google did not beat anybody. They came late. They came late, but they beat everybody because they used mathematics to get better solution. Okay, very multidisciplinary, very Basai kind of thing. Why? Because they were computer scientists, I think, coding programmer. But then you just say, okay, I'm going to be a programmer. I'm not going to look at math because I don't like math. I like programming. They actually go out and get the math. So whereas Alta Vista had very good program, they didn't look at math. They're not multidisciplinary. So they're not innovative. That's what we hope you guys are. If you're good in coding, look at math. By the way, if you go to the math department and you ask about this, they are not going to say, oh, it's a high level. It's like baby mathematics. Think about it, guys. The baby mathematics allows Google to beat everybody and be #1 internet platform today. All it took was that they opened their mind from just pure coding and programming and hey, what's available in mathematics? And it's not even advanced mathematics, guys. Okay, I can teach you how it's solved. It's also used determinant, but anyway, it's not that complicated. But the insight to look multidisciplinary, transdisciplinary into this, pick it up. Again, something not complicated from mathematics world, use it in an algorithm, beats everybody. That's what I want you guys to do. Okay? That's what I want you guys to do. Because you're not going to be a brilliant mathematician. You're not going to be #1 coder. You're not going to be a programmer. But you're going to have this kind of multidisciplinary thing. That's what I want you guys to have. Okay? So, with that, ran a bit over. Sorry about that. Let's finish today. When we come back on Monday, I'm going to go back again to the mechanics, but I'm going to start with calculus now. With calculus, we go to probability on Wednesday. Okay? Then on Friday, the same period, I will use as an introduction to applied digital intelligence. Now, there's my session on Friday. There's going to be 3 more sessions for introduction to sustainable development, smart city. I don't know what time those are because I'm not responsible for this. And then next Friday in the afternoon, we invited thinker from this discipline, not just computer scientists, to come have a seminar on what happens to the AI space. Are we ready? Okay. So that's actually very important. That's kind of sponsored by Nanspandi, Royal Society. As you know, our director, Professor Warsak, is a Rajpati. So that's in the afternoon. Encourage you to join that. I think by I'll find out. I have to be there. So it's either Zoom or big group. Okay. So I'll see you guys on Monday. Okay. Bye.